This is my voiceover narration for the second set of introductory slides in our course. Um, the slides are posted to Blackboard, and they do have um, a little bit of commentary as notes underneath the slide, which you should be able to view in PowerPoint. Um, if you don't want to sit through this video or listen to this recording, the information in those comments, on the slides, and in the selection from Roundtree, those pages that I scanned and posted, should be enough to get you through the quiz and to cover the material. But for those of you who would find it helpful, I am doing a screen grab and I'm going to run through these slides. I'm not going to read from the slides, um, every word, but I'm going to try to give a little bit of commentary. Maybe some thoughts don't make sense to type them out, but worth mentioning all the same. We spoke about latitude and longitude on Monday, ways that we measure absolute location on the surface of the Earth. Latitude and longitude are angular measurements, kind of measuring an angle up from the equator, measured from, I guess, the center of the Earth, or east to west, here again, from the center of the Earth, but in a different orientation. There were globes, a round globe that you've seen. It's pretty much the most accurate way that we have to approximate the surface of the Earth as a thing. Um, it's the real Earth isn't perfectly spherical, um, just by virtue of orbiting is a little flatter around the poles, but for all intents and purposes, the globe works. And important geographical properties are preserved: distance, direction, shape, area. So when I say those properties are preserved, I mean distance as measured on the surface of the real Earth can be approximated on the surface of the globe with accuracy. So that we talked about scale as being a descriptor of the difference in distance between real world and a model. We talked about it with maps, but it works for globes too. And in fact, globes have one scale that covers them entirely. So if you wanted different scales in a globe, you'd need to make a new globe, different size. There are, of course, some problems with globes: the size, portability, and that might include maybe storage. Just easier to fold up a piece of paper than to deal with a globe. We'll get into GIS later, Geographic Information Science, which makes use of computational power to model spatial processes. But actually, computations are a lot easier when we're thinking in two dimensions as well. So the process of taking data that's best represented on a globe, a spherical object, and turn it into a map involves mathematical transformations called projections. And there are different transformations that we can do in order to try to preserve different spatial properties of the Earth's surface. Those again, direction, distance, shape, and area. So the process of projecting spatial data involves the concept of a developable surface. So think of this as a surface that is flat, that can be made into a map or could be shown on a computer screen with ease. Developable, that kind of vocabulary, comes from the idea of film surface, of projection, like projecting light. So if you have a movie projector, just kind of one of these devices, there's a light source. It interacts with changes to color, really. And then there's a surface onto which those images are projected. So if you're setting up to watch a movie, it'd be a wall. Um, Here, the nature of that surface can vary and has implications for the spatial properties that a given projection will preserve. So here are three types of developable surfaces. One, cylindrical, another conic, and another planar. So I mentioned projecting. Think of it as a light source, an intermediate object, and then a wall or something onto which those differences are projected. Think of the light source as being right in the center of the globe, and it's putting light out in all directions. The light is interacting with here continents, I suppose, and then the shadows would be projected up onto a surface. And is that surface wrapped around the equator, like this cylindrical projection? Is it a cone wrapped around the globe but touching it along another parallel of latitude? Or is it planar? Here, just a flat surface to begin with. So this is kind of like a wall, say. So I mentioned that the globe preserves the highest degree of accuracy of these spatial properties. Using different map projections allows you to preserve the accuracy of some of them, but you're inevitably going to get distortion in others. I'm going to run through a few of these just so we can catch up on some vocabulary about this. So there are many different types of map projections, or there are many different projections, I should say, but they can be grouped into a few types, depending on the properties that they preserve the accuracy of. If the shape of objects is preserved, call that a conformal projection. So conformal, it's kind of with or similar shape, form here. And so this image is a Mercator projection. And you can see these horizontal lines are latitude parallels, which we know that their vertical distance remains essentially the same from the equator to the poles. But here, the increasing space between them suggests some sort of distortion of this map. I mentioned it on Monday. This is the type of map, this is the type of projection that gives you a gigantic Greenland that's as big as Africa. It's not really as big as Africa, it just looks like it here. And it's not that this projection is totally useless. The shape of Africa on this flat surface is essentially what the shape of Africa looks like on the globe. Similarly for Greenland. So the size is different, but the shape is the same. One way this is shown, I mentioned the spacing of the parallels, is you might see these circles drawn at different latitudes on here a globe, and to see what they look like here in the projected map. So the idea that circles of the same size and shape would look like this in a Mercator conformal projection. So the circles are still circles. They haven't been turned into ovals or anything. But the circles at higher latitudes are much bigger than at the equator. Some projections preserve direction. This includes the planar projections. So not the cylindrical, not the conic, but the planar projections. Here is a planar projection that accurately shows direction from the North Pole. So that preservation is going to be specific to a type of place. And you might call those azimuthal projections. If area is the spatial property that is most essential to preserve, then an equal area map, kind of nice when the word is in the term, is one to choose. So here the relative size of regions are preserved everywhere. And unfortunately, just by virtue of taking a globe to a flat surface, you can't preserve shape and area. So here, Greenland is not tiny, but it's tiny compared to Africa, which is a gigantic continent. But especially at the edge of this map, and especially I think east-west edge, you get shape distortions. So here, Alaska, if you can see it, is more diagonally stretched or sheared compared to what its real shape is. But the area is accurate. These next few slides show you tables. You don't need to memorize these or anything, just what to take from them. You might want to use it as a reference. If you ever need to make a map and to choose a projection, you'll have a lot of different choices. Here, what is that, about 20 choices? Cylindrical, planar, conic. And you can see that certain properties are preserved by these, others aren't, but that a lot of these different projections that preserve a property preserve the same one. So we have Mercator, transverse Mercator, oblique Mercator. They're all preserving shape. They just do so in different ways. Really, what you can do with these is by deciding for a Mercator or transverse or oblique, is decide which area on the surface you want to minimize that distortion for. In Mercator, the distortion around the equator is actually fairly low. But when you get to northern, high latitudes, north-south pole area, it's very high. But that's something for maybe a more advanced class or a class in which you would actually make maps. Here's some more information as a reference, not on the spatial property to be preserved, but actually this really the loosely termed spatial scale at which you'd want to map. If you're working at world scale, you would have a few different choices. If you're working at continent scale, national scale, say, you'd have a few more. Here's a third table indicating suitability of these different projections for different map types. So topographic maps showing change in elevation, geological maps showing what kind of bedrock or maybe soil type is present at different locations, thematic maps. These maps can show variation in any kind of variable, statistics, those kind of things. Presentations, navigation, and USGS maps, which are typically topographic maps, but maybe at different scale. Next, I'll talk about geographic information science. Acronym, typically, I just say GIS. It's a little bit confusing because geographic information science as a field encompasses a few different areas of technology and of really technological application, people doing things with the tech. And one specific component is called geographic information systems. So sometimes you'll see systems, geographic information systems, expressed as GIS. GISci could be the shortened form of geographic information science. It's important to know that these are two different things, but rarely, because GIS is a component, but the main component usually don't run afoul of that too much. So GIS science, there's some parts of it are new in geography, in that they weren't really done before really the advent of computers. Talk about the last maybe 50 years, more 40 or even 30 years. But then other aspects of GI science are really just re-examinations or reimagining of things that have been done for hundreds of years. Things like cartography, map making, or geodesy, which is kind of the field that attempts to model, but also to make accurate measurements of what the Earth really looks like. So it's not a perfect sphere. I mentioned that it's essentially flattened toward the poles, but there's also a lot of continental or regional scale variation. And so geodesists strive to detect that variation and also to model it, to make it useful. So here, main components: cartography, remote sensing, GPS, and GIS. So cartography, in short, the study and practice of making maps. Um, it's it's an essential component of GIS, um, but it's not necessarily tied to GIS. So as I mentioned, this is something geographers have been doing for hundreds of years. Exploration, um, tracking changes. Nowadays, I suppose we can do things, or we can measure and understand properties that change quicker. And so maybe some of the aesthetic concerns are more pressing. So really, what looks better, not just what you prefer, but maybe what helps people understand the data better. A remote sensing. This is a field concerned with acquisition of information about objects without actually making physical contact. Um, Within GIS, typically refers to the practice of obtaining data from satellites, using satellites um, to observe properties of the Earth system. This could be the surface of the Earth, it could be the atmosphere, clouds or water. Um, Also aerial data. So some sensors are maybe small enough you can put it on a plane or a drone and take images. There's some history of remote sensing, um, beyond the last 50 years, but it looked a lot different then. You'd have some sort of military applications in the Napoleonic era, like people going up in hot air balloons to survey the land, um, or spy satellites, not even satellites, but high altitude flight in World War II era, early Cold War, things like that. GPS is a technology and a system that allows us to, with much greater precision, understand absolute location on the surface of the Earth. And it does so with a network of satellites orbiting around the Earth um, that can receive information from transponders or handheld devices um, that are in view of multiple satellites in the global positioning system, so in that constellation. And based on multiple readings and an understanding of where those satellites are with respect to the surface of the Earth, location can be pretty precisely determined. And it used to be much more difficult to make use of these data, but nowadays, even smartphones have capacity for this. A lot of times, location in smartphones is based on the kind of nearby Wi-Fi networks, but they also have GPS capability. So then a GIS, a Geographic Information System. This is a computer system for capturing, storing, querying, analyzing, and displaying geospatial data. So in terms of these words, querying might be one that you're not familiar with. That just means essentially selecting certain data records from your entire database in order to find out statistics about that smaller group or to process those data in some way. So, kind of, if you're not interested in all the counties of the US just in Alabama counties, that would be a query you could do. Select only Alabama counties. I'll mention something about this graphic. When you see descriptions of a GIS, you often see these kind of two-dimensional layers superimposed on one another. And the GIS is valuable because it does allow you to examine what is in different places and what is with respect to a lot of different things. Here we have social factors, biodiversity, engineering, land use, environmental considerations. You might get caught up because some of these data might come from very different sources. They might be generated in different ways, maybe even have different scales. But just the ability to ask those questions can be very powerful. Certain variables might change a lot over time, others might be fixed. The other thing to remember is not just the layers, but essentially this arrow, and the arrow hitting the layers at the same correct point. And what I mean there is it's referenced. It's referenced to the same location. So if you look in a map book, you can find a lot of different maps, but it might not be so simple to, I don't know, cut out pages and try to layer them on top of one another and trace, because you're not certain exactly how they should line up. They could be made at different scales. The GIS, or the thing about the GIS that's very powerful is that it handles that for you. There's some examples of application. Here, looking at disaster impact, the Indian Ocean affected by tsunami. So things like country locations very rarely change, but when you have a natural disaster, that's typically a quick moving, unexpected accident. And so making new maps like this, where different areas were affected the most, what else was present there, can be very interesting. Crime analysis. So crimes can happen different places. There's going to be kind of some certain base level of crime over time, but if you can see where it happens, you might better understand why it's happening or how to deal with it. Again, here looking at power outages. So we have county boundaries for an area around Buffalo, New York. Those county boundaries aren't really going to change, but something that would change is the percent of accounts, I suppose, without electrical service at a given moment in time. So this is a thematic map of where the outages were most severe. Something else that would change would be the condition of roads. So the road locations, some roads might get built every now and again, but the network is the network. But if there's a big snowstorm up in Buffalo or a hurricane and you've got downed trees, condition of the roads can be incredibly important to identify. Here again, related to that percent of debris that would be cleaned up at a time. So in these slides, meant to just explain to you the concept of map projections, or moving toward a relatively accurate globe to a less accurate but more useful two-dimensional map. Also to explain some of the basic components of GI science.